This video is Module 11, Part 1 of 2 for the Intro to Networks, Version 7 for the Cisco Networking Academy. We're going to be covering IPv4 addressing. In this video, which is Part 1 of 2, Part 2 of 2 will have a link in the description below. We're going to look at an IPv4 subnetting scheme and how we segment that scheme. We're also going to look at address structure. We're going to look at IPv4 unicast, broadcast, and multicast. And we're going to look at types of IPv4 addresses and then also network segmentation. So on the IPv4 address structure, we have a network and a host portion. A v4 address is a 32-bit address that is made up of a network portion and a host portion. The network portion is what all of the other IP addresses can see, and the host portion is your ID for that particular host. So when we determine the network portion versus the host portion, we need to look at the 32-bit stream of ones and zeros that are coming in. A subnet mask is used to determine the network and the host portions. When we look at this, the 192, this is our v4 address here, and I'm just going to call the IPv4 v4, and I'm going to call the IPv6 v6 for simplicity. It's easier for me to say that. When we look at our IP address and we convert it to bits, ones and zeros, we get 32-bit length. So this 192 gets converted to a 11000000. 168 gets converted to this, 10 gets converted to this, and then this host portion here is our 10, and it's 00001010. Let's take a look at that with the subnet mask. When we identify the network and the host portions with the v4 address, the subnet mask is compared to the v4 address bit for bit from left to right. I know we write out IP addresses and we write out binary and right to left, but when the network is reading these bits, they read them from left to right. So when we read these, we read them from left to right here. This one is our same number we were just looking at. And our subnet mask in this case is 255.255.255.0. So what is that telling us? That's telling us that 255 is all ones, 255 is all ones, 255 is all one, and then we get to the first zero. So what happens is the network starts reading the subnet mask, and it goes through and it sees all of these ones. And when it gets to the first zero, the network says, oh, okay, everything to the left of this zero here is the network. You cannot have any other zeros over here. So you have to have 255, 255. If you had a zero here, the network portion would be right here, and everything to the left would be the network. So when it gets to the first zero, it's going to say everything to the left is the network and everything to the right is the host. That's one of the concepts that's sometimes difficult to catch on to at first. At least it was for me. So all you have to do is remember that your subnet mask is all ones up until the point that it becomes the first zero, and then everything to the left is network, everything to the right is your host. Simple as that. So the actual process of identifying the network and the host portions is called ANDing. And I'm going to have links in the description below to how to subnet in the fourth octet, how to subnet in the easy range, how to do more advanced subnetting, and how to do ANDing subnetting, and as well as VLSM or variable link subnet mask. Those links are going to be in the description below. Those are other videos that I've created a couple of years ago. They work pretty well. They're a little bit cruder than what I would do now, but they still work well, so you can check those out if you want to learn a little bit more about subnetting, which you do need to know for this course. The prefix length is a less cumbersome method used to identify a subnet mask address. So the prefix length is a bit set to 1 in the subnet mask. Or the prefix length is the number of bits set to 1 in the subnet mask. That's what I was just telling you. So when it gets to 0, you know everything to the left is the network. It's written in slash notation though. So when we look at their prefix length here and we say a /8, and you're going to get this in networking. Somebody's just going to say, hey, I gave you a /24. They're going to give you this IP address right here. If I was to tell you what your IP address was, I would say 192.168.10.10/24. I wouldn't spell out or tell you this entire subnet mask here, because I know by saying a /24 that that's going to be a 255.255.255.0. I recommend learning how to do this prefix length and where your numbers are. It's really simple because your prefix length is how many ones you have, and you just count them up. So if your subnet mask is 255, that's your first octet. That's 8 ones. That's a /8. You add a second octet, that's /16. You add a third octet, that's /24. Just basic math with ones and zeros. Even me that has trouble with math can get this. So we have a /24, /25, /26. That just means that we're moving the network one bit over each place. If we had one where we had a 1 right here, that would be a /9. Now, determining the network using logical ANDing or AND, a logical AND Boolean operation is used in determining the network address. Logical AND is the comparison of 2 bits where only 1 and 1 produces a 1, and any other combination results in a 0. So a 1 and a 1 equals a 1, a 0 and a 1 equals a 0, a 1 and a 0 equals 0, a 0 and a 0 equals 0. It's the principle of if you add a 0 in, you're always going to get a 0. So, if you do anything with 0, it ends up with a 0. So 1 equals true and 0 equals false. So to identify the network address, the host v4 address is logically ANDed bit by bit with the subnet mask to identify the network address. When we look at our IP address here of 192.168.10.10 and our subnet mask of 255.255.255, we know that these are all ones. We add these together bit by bit. So we start saying 1 here, and then we get 0, 0, 0, 0, 0, and we come up with the same number, right? Because a 1 and a 1 equals a 1, a 1 and a 1 equals a 1, a 0 and a 1 equals a 0. So what is this number? 11000000? That's a 192. Same thing for the next octet. And the easy way to do this is if you have a 255 here, you automatically know that the ANDed number is going to be the same as your IPv4 address. So on this one here, we know our AND number, our network, is going to be the exact same as 192.168.10. You don't have to AND it. But that's what the routers or the networking devices are doing. They're taking each one of these IP addresses, or each one of these bits, and they're comparing them until they get to a point where they say 0 and 0 is 0, 0 and 0 is 0, and then 1 and 0 is 0. So they have a v4 network address. This is your network ID. This is how you can quickly get a network ID. You compare your v4 address with your subnet bit by bit, and your network address is 192.168.10.0/24 because you've got your subnet mask there. I've got an entire video in the description below that explains it a little bit better with detail. So check that out if you're still a little bit confused with the ANDing process, because this one is a little bit tougher to get. But once you get it, it's kind of like riding a bike. You're going to get it. When we look at the network host and broadcast addresses, within each network, there's 3 types of IP addresses. You have your network address, your host address, and your broadcast address. And this is looking at a network here. We have our router, our edge router. We have 192.168.10.1/24, 255.255.255. And then we have our network address here of .0. That's our network address. We put an IP address of 1 on our gateway address. And then we have .10, .55, .101, and 12. Even those are all within the range of that network. Those host numbers are all within the same network range, so they can all see each other inside this local area network. And this is a little bit different graphical representation of it here, where we have the subnet mask, the network portion, the host portion. They're all zeros and ones, and then this pulls it out. So we have our network ID. That's our network address. We have our host address. Those are all our host numbers. And then we have our broadcast address, which is, in this case, in this one, it's the last IP address in your host range. So your first number in your host range is your network ID. Your last one in your range is your broadcast ID. And in my video below, if you go check that out, on subnetting, it talks about when you subnet numbers out and two numbers always get subtracted, your network ID and your broadcast ID. IPv4, unicast, broadcast, and multicast. We've talked about these three terms before in previous videos. Unicast transmission is sending a packet to one destination IP address. One destination. The example here is PC 172.16.4.1 sends a unicast packet to the printer at 172.16.4.253. It's a one-to-one unicast. So this PC here says I need to print, it sends it across, it goes to the switch, and it gets to the printer. A broadcast is sending a packet to all other destination IP addresses. So this PC here, 172.16.4.1, sends a broadcast packet to all v4 hosts. It goes out, it goes to the router edge, it goes to all of the switches here, and it goes to all the devices, and it just goes to all the devices. A multicast transmission is sending a packet to a multiple address group, but not all of the addresses. So this one here is sending a multicast packet to the multicast group of 224.10.10.5. It goes out and it sends it to multiple units. It doesn't go to the router, it doesn't go to the printer, it just goes to those two particular computers. Types of IPv4 addresses. We have public and private v4 addressing. RFC 1918 addresses public v4 addresses. Those are globally routed between internet service provider routers. Those get seen by people outside your local area network or routers outside your local area network. Private addresses are common blocks of addresses used by a lot of organizations to assign v4 addressing to internal hosts. So I could have a block of private addresses that are the exact same as yours on your private addressing, but they would never see each other and they would never collide because they're not public. Private v4 addresses are not unique and can be used internally within any network, and private addresses are not globally routable. This RFC 1918 private address range is the range where it says should be internal, the 10.0.0.0/8, the 172.16.0.0/12, and the 192.168.0.0/16. You need to memorize these. These are going to be on exams. You need to know these ranges, and you need to know these range of numbers. They are on the Cisco Academy exams. They are on the CompTIA networking exam. I don't think they're in the CompTIA A+ exam. I don't remember them being there, but they are on the Networking Plus exam, and they're on the Security Plus exam as well. Routing to the internet. Network address translation translates private v4 addresses to public v4 addresses. NAT is typically enabled on the edge router connecting to the internet, and it translates internal private addresses to public global IP addresses. There are special use v4 addresses. We have the loopback addresses. It starts at 127.0.0.0/8. So they go all the way up from 127.0.0.0.1 all the way up to 127.255.255.254. It's commonly identified as only 127.0.0.1. If you're wanting to test your local NIC, your network interface device, you would ping it by doing ping 127.0.0.1, and that would let you know if you get a reply back, you know that your network interface card is working, or at least it's giving you a reply back that it can communicate out. There are link local addresses, 169.254.0.0/16. That's commonly known as the API PA, or the automatic private IP addressing. It is used by Windows DHCP clients to self-configure when they cannot find a server. So if a Windows client boots up and it cannot find a DHCP server, it will go ahead and assign itself an IP address in this range so that the network card can at least have networking ability it will not be able to see anything that is connected to on a local area network unless that is in that range on that local area network, in that host range. But at least it boots up working. There was once a thing called legacy classful addressing. RFC 790 allocated v4 addresses in classes. We had class A, B, C, D, and E. You only used A, B, and C in production. You could assign class A addresses. Typically, your ISPs would give out class A addresses, and then smaller areas would give out B, and then you would get your class Cs for your local area networks. The problem with it is it wasted many IPv4 addresses, and it's been replaced with classless addressing, which we just use the slash rules now. It ignores all the rules of the class A, B, and C. You still want to memorize these classes, the starting to ending. So these are class A is all your /8s. These are all your /16s. These are your /24s. And then you need to know your class D up to class E. Even though these were never used in production, you may still have someone that asks you a question on what class an IP address is in. The proper response is to say, in today's networking world, we no longer use classful addressing. It's been replaced with classless addressing. But the answer to your question is, that's a class B address. So you know the answer, but you're also correcting them and letting them know that, hey, we don't use classful addressing anymore. So who assigns IP addresses? The Internet Assigned Numbers Authority, or the IANA, manages and allocates blocks of v4 and v6 addresses to 5 regional Internet registries, or RIRs. In North America, it's the ARIN. And the RIR, or in North America, the ARIN, is responsible for allocating IP addresses to the ISPs, Internet Service Providers, who provide those v4 and v6 addresses to smaller ISPs and to organizations. Think of Microsoft, Amazon, Verizon, Comcast, the big, large companies that would get big blocks of ISPs and then use those in their networking. Network segmentation. Broadcast domains and segmentation. A lot of protocols use broadcast or multicast. ARP or ARP uses broadcast to locate other devices. Host send DHCP discover broadcast to locate a DHCP server. And switches propagate, or they forward, broadcast out to all interfaces except the interface on which it was received. The only device that stops a broadcast is a router. Routers do not send forward broadcast request, and each router interface connects to a broadcast domain, and broadcasts are only propagated within that specific broadcast domain or local area network. There are problems with large broadcast domains. One problem with the large broadcast domain is that host can generate excessive broadcast and negatively affect the network. The solution is to reduce the size of the network and create smaller broadcast domains in a process what we call subnetting. If you check in the description below, I have links to videos on subnetting v4 addressing. I've talked about it in previous slides here, and I'm going to tell you again, they're below. They're helpful. Check those out. We divide the network address, for example here, 172.16.0.0, into 2 subnets. If we look at our example up here, we've got all 400 users in one subnet, and all of that traffic can generate a lot of bouncing around, and it can negatively affect getting information. So we split those off into 2 subnets, or we segment that network into 2 smaller networks, and now we have 200 users here and 200 users here. We have them on each side of a router, but we technically could put them on, use a switch to do the same thing. We can do a VLAN, a virtual local area network, and we can use the subnetting or segmentation to do the same thing. Subnetting reduces overall network traffic. It improves network performance. It can be used to implement security policies between subnets. It reduces the number of devices affected by abnormal broadcast traffic. And some of the reasons might be a location. So we might want to have different levels of a building to have different subnets, 5th floor, 4th floor, 3rd floor. Groups or functions, we might have the sales department not being able to see the accounting department, or students not being able to see the administration or maybe the faculty area. And we can also segment out by device types. So let's say that we wanted to have servers over here on one segment and we didn't want users to be able to see everything on the server, just be able to ping maybe a file server or a print server and just send requests. So we could put that on its own subnet. This has been Module 11, Part 1 of 2 on IPv4 addressing. I hope the information was helpful. Stay safe and be excellent to each other.